Every single second you're online, there's this unsung hero in the background making it all happen. It's a fundamental piece of the internet that you use constantly, but you probably never, ever think about it. Well, today we're going to change that. We're diving deep into the data link layer. And the crazy thing is, the core idea is actually pretty simple. Just imagine a local postal worker, right? They don't care about getting a package across the entire country. Their only job is to get that letter from your mailbox safely and reliably to the next house or the next post office on the block. That's it. And in our digital world, that's exactly what the data link layer does. So why do we even need this digital mail carrier? Well, because without it, our networks would be just complete and utter electronic chaos. The layer right below it, the physical layer, that's just a raw, messy jumble of electrical signals, ones and zeros flying down a wire. Something has to step in and bring some order to that madness. And bringing order really boils down to solving two huge problems right off the bat. First, how do you give this chaotic stream of bits any kind of structure? And second, how can you be sure that what you send is actually what gets received on the other end? Think about it. Imagine trying to read a book that has no spaces between words, no punctuation, no chapters, just a single endless line of letters. That's exactly the challenge a network device faces. It's looking at this endless river of ones and zeros, and it has to ask, where does one email end and the next chunk of a video stream begin? Well, the solution to this chaos is a really elegant and absolutely essential concept, and it's called framing. Framing is literally the act of taking that raw stream of data and putting it into digital envelopes. Each one of these envelopes is called a frame, and it has a very clear start and a very clear end. So now, instead of that endless, confusing stream, the receiver gets these neat, organized packages it can actually understand. Okay, so our data is in neat little digital envelopes. That's great. But what happens if, on its journey, that envelope gets rained on and the ink starts to run? In the digital world, that rain is electrical noise or interference corrupting our ones and zeros. How would we even know if the message arrived damaged? To solve this problem, the data link layer has another brilliant trick up its sleeve, and that's error detection. So here's how it works in a nutshell. Before sending a frame, the sender does a quick calculation on the data and creates this unique digital fingerprint, often called a CRC, and it attaches it to the frame. When the frame arrives, the receiver does the exact same calculation on the data it got. If the two fingerprints match, perfect, the data is good to go. If they don't match, it knows the frame is corrupt and it just throws it away. Simple as that. But, just making sure a single message gets there correctly, that's only half the battle. Networks aren't just about one-way deliveries, they're about conversations. And for that, the data link layer has to be this master diplomat, making sure everyone cooperates and plays fair. Let me paint a picture for you. Imagine you've got your brand new, lightning-fast computer. You want to print a big document, so you hit print and fire that file across the network. But the device you're sending it to is your trusty old printer that you've had for like 10 years. It's slow, it's got a tiny little bit of memory, and there's just no way it can keep up with your new machine. So your computer is just blasting data like a fire hose, but that old printer can only sip it through a tiny straw. Without some kind of control, the printer's little memory buffer is going to overflow in a fraction of a second, and most of your file will just vanish into thin air. And the solution to this super common problem is something called flow control. This is basically the printer's ability to hold up a little digital hand and tell the computer, whoa, slow down a sec. It lets the slower device control the pace of the conversation, making sure it never gets overwhelmed with data. It's a simple idea, but it's absolutely vital for reliable communication. All right, so we've solved the problem for two devices talking to each other. But what about a modern Wi-Fi network? You've got your laptop, your phone, your smart TV, maybe your fridge, all sharing the same airwaves. What happens when everyone tries to shout at the same time? Well, you get chaos, a digital shouting match. And to prevent that, we need our final key service, access control. Think of access control as the network's traffic cop. On a Wi-Fi network, for instance, the rule is basically listen before you talk. A device literally checks if the air is clear before it tries to send anything. On older wired Ethernet, the rule was a little different, more like speak, but listen for collisions. If two devices talked at once, they both stop, back off for a random amount of time, and try again. But the goal is always the same. Make sure only one device is talking at a time on that shared channel. Now, this all brings up a really key point. The data link layer is smart. It actually uses different sets of rules depending on the kind of network or, the playground it's operating on. So, on one hand, you have what's called a point-to-point link. Think of it like a direct phone call between you and one other person. It's a simple, private conversation. But then you have a broadcast network, like your home Wi-Fi. That's more like a crowded party where everyone can hear everyone else. In that kind of environment, you absolutely need addresses, like MAC addresses, to know who a message is for. And you definitely need that traffic cop, that access control, to keep everything from descending into chaos. Okay, so we've talked about framing, error detection, flow control, access control. What's the ultimate point of all this? Well, it all comes down to one of the most powerful and beautiful ideas in all of computer science: abstraction. See, the real goal, the true purpose of all these complex functions is to take a messy, noisy, totally unreliable physical connection, a copper wire that's susceptible to interference or chaotic airwaves, and transform it into a clean, reliable, and predictable channel for communication. It hides all that physical world chaos. The layers that sit on top of it, like the network layer that deals with your IP address, they don't have to worry about electrical noise or data collisions or any of that messy stuff. They get to live in this perfect, clean world, all thanks to the incredible hard work of the data link layer down below. So the next time you stream a movie or send an email without a single error, take a second to remember that unsung hero. The digital postal worker, the diplomats, and the traffic cop all rolled into one.